The universe is full of light, motion, and energy today, but physics suggests that this activity will not last forever. Scientists have proposed a chilling possibility known as the heat death of the universe. This idea describes a far future where the cosmos becomes dark, cold, and lifeless. Stars will stop shining, galaxies will grow quiet, and all processes that require energy will slowly fade away. It sounds dramatic, but it comes from one of the most basic principles of physics, entropy. As time moves forward, entropy increases, meaning energy spreads out and becomes less useful. Over unimaginable stretches of time, this gradual change could transform the vibrant universe into silence. To understand heat death, we must first understand entropy. Entropy is a measure of disorder or randomness in a system. In physics, the second law of thermodynamics states that entropy in an isolated system tends to increase over time. This means energy naturally spreads out rather than concentrating in one place. Think of a hot cup of coffee left on a table. Over time, it cools because its heat spreads into the surrounding air. The universe behaves in a similar way. Energy that once powered stars, galaxies, and cosmic events slowly disperses. Eventually, this spreading of energy may lead to a universe where no organized processes remain. At the present moment, the universe is filled with powerful engines of energy such as stars. Inside every star, nuclear fusion converts hydrogen into heavier elements, releasing enormous amounts of light and heat. This energy fuels planets, climates, and possibly life itself. However, stars do not shine forever. They depend on limited fuel stored in their cores. Over billions or trillions of years, this fuel gradually runs out. When that happens, stars either collapse, explode, or fade into dense remnants like white dwarfs or neutron stars. As more stars reach the end of their lives, the universe slowly becomes darker and less energetic overall. Galaxies, which contain billions of stars, also evolve with time. In the early universe, galaxies actively formed new stars from giant clouds of gas and dust. Over time, however, this gas becomes depleted. Without fresh material, star formation begins to slow down. Astronomers believe that trillions of years from now, most galaxies will have used up nearly all their star-forming gas. The brilliant birthplaces of stars will become quiet cosmic museums, filled mostly with aging stellar remnants. When new stars stop forming entirely, the universe will enter an era where only the long-fading glow of ancient stars remains. After star formation ends, the universe enters a long period sometimes called the degenerate era. During this stage, most visible stars have already burned out. What remains are compact objects such as white dwarfs, neutron stars, and black holes. These remnants still contain matter and energy, but they no longer shine brightly. Over trillions of years, they slowly cool and fade. White dwarfs gradually lose their remaining heat, becoming dark stellar corpses, sometimes called black dwarfs. The cosmos at this point would look very different from today, with very few sources of light scattered across enormous distances of empty space. Black holes, the most mysterious objects in the universe, also play an important role in the story of heat death. For a long time, scientists believed black holes would last forever. However, theoretical physicist Stephen Hawking discovered that black holes slowly lose energy. According to this theory, black holes emit tiny amounts of radiation and gradually shrink. This process is incredibly slow, but eventually, even the largest black holes evaporate. Their disappearance would mark another step toward a colder and more empty universe. As trillions upon trillions of years pass, the universe becomes increasingly quiet. Without stars to produce heat, temperatures drop closer and closer to absolute zero. Only faint radiation and scattered particles drift through the vast darkness. Galaxies themselves may gradually break apart as gravitational interactions slowly fling stars away. Over unimaginable timescales, matter becomes more widely spread and organized structures disappear. The once spectacular cosmic web of galaxies fades into a sparse collection of isolated particles. Entropy continues increasing throughout this process. Every interaction and radiation emission spreads energy more evenly. The universe moves toward a state of maximum entropy. In such a condition, energy still exists, but it is distributed so uniformly that no useful work can be performed. Machines cannot run, and life cannot survive. The difference between hot and cold regions disappears. Without these differences, nothing drives motion or change. The universe becomes a quiet equilibrium. One of the most astonishing aspects of the heat death theory is the timescale involved. The final stages may occur after around 10 to the power of 100 years. Compared with these immense timescales, the entire era of stars and galaxies that we observe today represents only a brief moment in the lifetime of the cosmos. Scientists study the possibility of heat death using observations of cosmic expansion. Our universe has been expanding since the Big Bang, driven by dark energy. As space expands faster and faster, galaxies move farther apart. Eventually, many galaxies will drift beyond the observable horizon, meaning their light will never reach us again. The idea of heat death was first seriously discussed in the 19th century. Early physicists realized that if the universe followed thermodynamics, it might reach maximum entropy. Some scientists have proposed other possible endings, such as the Big Crunch or the Big Rip, but heat death is quieter and slower. It is a gradual fading. Although heat death sounds bleak, remember it lies unimaginably far in the future. Our sun itself will become a red giant in about 5 billion years, transforming the solar system. By the time the heat death era begins, all current stars will have evolved. Civilizations, if they exist, would have timescales of trillions of years to adapt. Heat death also highlights an important idea about the nature of time. The direction we perceive as the forward flow of time is closely related to increasing entropy. When entropy grows, processes appear irreversible. A broken glass does not spontaneously reassemble. As entropy increases, systems move from order toward disorder. Modern cosmology continues to investigate whether new physics could alter this outcome. Some theories suggest unknown processes might change how energy behaves. Others explore the possibility that new universes could form through quantum fluctuations or cosmic cycles. Many mysteries remain unsolved. The concept of heat death highlights how precious and unusual the present era may be. We live during a time when stars shine brightly and galaxies interact. Understanding the potential fate of the universe helps physicists test fundamental theories. It invites us to appreciate the dynamic cosmos we inhabit today. From the burning cores of stars to the quiet drift of particles, everything follows the same laws. While the end may seem distant, it reminds us of the power of physics. Thanks for watching.